Hey everyone, welcome back, and thank you for joining us again in our next discussion of statistics. Heading into our objective then, we're going to test hypotheses regarding matched pairs data. And make sure we have this in mind, because this is after we've recognized that we have matched pairs data. We have to be able to recognize that from the problem presented to us. The overall concept here is, when we do statistical inference on matched pairs data, we actually use the same methods that we did on a single population mean, with the exception that the differences, emphasis on the plural there, are analyzed. We'll explain that more within the example. First are requirements that need to be met. To test the hypothesis regarding the mean difference of matched pairs data, the sample has to be a simple random sample. The sample data have to be dependent or matched pairs. And here's the big idea, the differences from our data have to be normally distributed with no outliers, or the sample size n has to be large. Take note that our sample size is the number of differences that we'll have, not the total pieces of data that we'll have. Heading into our steps on how to conduct the hypothesis test then, of course we need to determine the null and alternative hypotheses first. The hypotheses can be structured in one of three ways, where mu sub d is the population mean difference of the matched pairs data. We need to make note of this because we're only using mu sub d here when we're working with matched pairs data. It implies the mean of the differences of our data. With the exception of mu sub d being different, notice our hypotheses are just like when we had a single population hypothesis test. We have mu sub d equal to 0 as our null hypothesis, regardless of the situation, that is left-tailed, right-tailed, or two-tailed, and then mu sub d not equal to, less than, or greater than, based on the type of test that we're conducting. So we're still comparing to some value now, as opposed to one population to another. Step 2, of course, would be to recognize alpha that's typically given to us from the story. Step 3, as we've seen before, would be to calculate the test statistic, and now we've got t naught, so we're working with students' t distribution again. Notice d bar and s sub d are the mean and standard deviations of the differences from our data, because remember we're going to be comparing matched pairs data. After our test statistic, we need to find the p-value using the t-CDF function again. And of course we need to be careful with our two-tailed test and make sure we double the area under one of those tails. And remember to use the t-CDF function. We input t-CDF, our lower and upper bound, but then we need to include those degrees of freedom. Of course, once we have our p-value, we need to state the conclusion. And like we've seen before now, if the p-value is less than alpha, we know to reject the null hypothesis. Heading over to our example then, we're told the following data represent the cost of a one-night stay in Hampton Inn hotels and La Quinta Inn hotels for a random sample of 10 cities. Test the claim that Hampton Inn hotels are priced differently than La Quinta hotels at the alpha equal to a 0.05 level of significance. Well, first we want to recognize that we've got matched pairs data since the hotels come from the same 10 cities. That is, we're not comparing the group of Hampton Inn hotels to the group of La Quinta hotels. Instead, we're comparing the price difference between the Hampton and La Quinta hotels in Dallas, and then again between the two hotels in Tampa Bay, and then again in St. Louis, and on down the list, but the idea being we've got direct comparisons of hotel to hotel, not group to group. That means to test the hypothesis, we first need to compute the differences and then verify that the differences come from a population that is approximately normally distributed with no outliers because we've got ourselves a small sample size. So to compute the differences, we're going to go ahead and throw our Hampton Inn data into L1 and the Quinta data into L2. And then like we've done a while back, we're going to define L3 as L1 minus L2 and allow the calculator to populate our L3, which will be our list of differences. Heading over to our calculator then, I'm hitting Stat and then Edit to get into our lists. I've put data into my L1 and L2 already. Going up to L3, I'm going to hit Enter to define L3, and we're defining L3 as L1 minus L2. Hitting Enter, it will compute the differences for us from each row, and L3 now represents our list of differences. Now that we have our list of differences in L3, we need to check our requirements. Remember, since the sample size is small, we have to verify that the differences come from a population that is approximately normally distributed with no outliers. Again, our emphasis is on the differences, not the raw data itself. The rest of our analysis is on the differences as opposed to the original data presented. Well, to confirm that we've got a population that is approximately normally distributed, we make a normal probability plot of the differences, which we've done before, and looking at the plot that's provided for us, we see that there's no violation of normality assumption, so we can assume that we've got an approximately normal distribution. Remember to check outliers. We use a box plot. So looking at the box plot of the differences again, we see no outliers. which means we're all set, and our requirements have been met. Heading into our hypothesis test now. Remember to be careful with our null hypothesis. This is matched pairs data, so our null hypothesis H0 would be mu sub d equal to 0, showing the reader that we're working with matched pairs data. And since we were told to test the claim that Hampton Inn hotels are priced differently than La Quinta hotels, we've got an alternative hypothesis of mu sub d not equal to 0, and this is a two-tailed test. We were told alpha is equal to a 0.05, and now we can calculate the test statistic that is T0. Well, in order to calculate T0, we need d bar and also S sub d. Remember, d bar, by definition, is the mean of the differences. So we can get the mean of the differences by using our 1var stats. Make sure we're careful though, the 1var stats would be of L3, since L3 would be our list of differences. Heading over to our calculator to make sure that this is all clear. Remember, L3 was our list of differences, so we're going to do the 1var stats of our differences, which would be in L3. When we do 1var stats, remember we're looking for d bar, that is the mean, or our calculator doesn't know that, so x bar represents the mean of the differences. That means we know x bar is representing d bar in context of our formula. At the same time, we also have s sub x, which represents the standard deviation of the sample of differences that we have, and that means we also have s sub d. So s, our sample standard deviation, would be the standard deviation of our differences, so we've got both d bar and s sub d from our 1var stats. Heading back to the notes then, from our calculator, we got d bar, which was x bar in our calculator, to be 53.4, and s sub d, which was our standard deviation from the calculator, is approximately 26.792. And the last variable we need for the formula would be n, our sample size. Well, n is 10, making sure we're careful that 10 would be the number of differences. We had 20 pieces of data from the original problem, but we have 10 differences. And that means n equals 10, since we're working with matched pairs data. That means we can calculate our test statistic T0, where we've got 53.4 as our d bar, divided by the quotient that is s sub d at 26.792, divided by the square root of our sample size that is 10. Inputting this in our calculator, we get approximately 6.30. And now that we have our test statistic, we can find the corresponding p-value using the TCDF function. Of course, first I'm going to draw the curve. Remember, we're working with a t-distribution, and we had a test statistic of a 6.30. Since this is a two-tailed test, we've got both a positive and negative end of that test statistic. Remember, to find our p-value, we need to do 2 times the TCDF of our test statistic that is a 6.30, and that would be the right side of our graph. So we're going 6.30 up to our positive infinity, and our degrees of freedom would be 9 since our sample size was 10. This gives us a p-value of approximately 0.00014. As per usual, comparing that to our alpha level of a 0.05. And that means we've got a p-value that is less than our alpha, so we get to reject our null hypothesis. And that means we can conclude that there is sufficient evidence to conclude that the Hampton Inn hotels and La Quinta hotels are priced differently at the alpha equal to a 0.0 level of significance. And we're all set with our hypothesis tests on the mean difference between two populations with matched pairs data. Heading into our next objective then, we're going to discuss the construction and interpretation of confidence intervals for the population mean difference of matched pairs data. Well, like we've done before, we have lower and upper bounds for our confidence interval, and we see the formulas on our notes. Notice now that we've got d bar involved, so we're still working with the differences from our data, and of course we can combine these to just do a plus or minus rather than separating the lower and upper bound. So let's go ahead and jump straight into an example. We're asked to construct a 90% confidence interval for the mean difference in the price of our Hampton Inns versus La Quinta hotel rooms. Remember, we've already verified that the difference data come from a population that is approximately normal with no outliers, and we have our data in our calculator already. Well, since we're constructing a confidence interval, we know our formula for that confidence interval needs to be used. Well, from our previous example, we know d bar, remember that came from 1var stats of our list of differences, is 53.4, and our standard deviation of that list of differences, which represents s sub d, was approximately 26.792. Of course, our sample size is 10 because we've got 10 differences, and that means we can substitute these values into our formula, and we just need to find our t sub alpha over 2. Well, to find t sub alpha over 2, of course we need to find alpha first, which would be the complement of our confidence level. So alpha is 1 minus our 0.90, giving us a 0.10, and that means alpha over 2 would be a 0.05. So to find t sub alpha over 2, we need t sub 0.05. Using the inverse t function as opposed to the inverse norm function, remembering to be careful with that, we've got inverse t of a 1 minus a 0.05 with 9 degrees of freedom since our sample size is 10. And that means our value for t sub alpha over 2 is approximately 1.83. Substituting our value of t sub alpha over 2 into our formula, we end up with a confidence interval with a lower bound of 37.869 and an upper bound of 68.931. And that means we're able to articulate our interpretation. That is, we are 90% confident that the mean difference in hotel room price for Hampton Inn versus La Quinta Inn is between $37.87 and $68.93. So wrapping up this discussion, remember we can check our hypothesis test results and confidence intervals using our calculators. Referring back to the Hampton Inn and La Quinta Inn hotel data, let's go back to the hypothesis test where the claim was that they were priced differently. Well, to conduct the test on our calculators, we're going to use the t-test function on the differences where we had those in L3. Take note that it's not a 2-sample test, instead it's just a t-test. Remember, we had L1 and L2 and we created a new list of just differences, and we've been working with the differences since then. Heading over to our calculators then, I'm going to hit stat, and then I'm going to go over to tests, and we see t-test as our second option. When we do our t-tests, we want to use data since we have our raw data. Our mu naught is 0. Remember, mu naught is mu sub d, and that's equal to 0. Our list is L3 for our differences. The frequency is 1 because we put our raw data into our lists. Our alternative hypothesis was not equal to mu naught because we've got a two-tailed test. And we can arrow down to calculate to get the results of our t-test. We end up with our t-statistic that was a 6.30, and of course there's our p-value. That is a 0.00014. Notice again that the test also gave us x bar and our standard deviation, where x bar represents d bar, remember it's the mean of the differences, and s sub x represents the standard deviation of our differences, so that means we've got s sub d. Heading back to the notes then, we saw our p-value in the calculator, and like we concluded previously, our p-value is less than the level of significance, so we got to reject the null hypothesis. So let's head over to part B where we're going to discuss the confidence interval. To construct a 90% confidence interval for the mean difference of our matched pairs data, we're going to use a t-interval. You see the steps on your notes. So heading over to our calculator one more time, we're hitting stat, and I'm going over to tests, and you see option number 8 is your t-interval. Hitting enter on t-interval, we still have the data in L3. We just need to make sure our confidence level is at 90%, which mine is, so I can hit calculate. Our calculator generates the confidence interval. We end up with our lower bound of a 37 and change, and our upper bound of a 68 and change like we did previously. Notice again, it still gives us x bar and s sub x, which would be representing our d bar and s sub d. Which means heading back to the notes, we're able to obtain the same interpretation we had previously, where the mean difference in the hotel room prices was between approximately $33 and change and $68 and change. And we're all set with conducting hypothesis tests and confidence intervals on our calculators for mean differences of matched pairs data. And thank you again for joining us.